Hello students, welcome to Akshara 8 Foundation. So today we are going to discuss one more topic which is left in the synopsis 3 sorry. So that topic is moment of inertia of the removed part or remaining part there, okay. So suppose let us see here the moment of inertia of remaining part. The moment of inertia of remaining part of a body. See here we'll take some example. So by the example we'll take here. Suppose if you take a disc here, so the moment of inertia of the disc about the axis passing through its center and perpendicular to the plane. So it has a moment of inertia, so that we know that it is mr square by 2. Okay. Suppose in this certain amount of mass has removed there. Okay. Let us consider here. So this is the amount of mass of the disc has removed. So this part has removed there. Now here it becomes like this. This part of the body has removed. Okay, there is the the moment of inertia of the removed part. Let us consider here it is removed there. So R, moment of inertia R there. Now the moment of inertia of the remaining part, the moment of inertia of the body remaining part. So then that remaining part, moment of inertia of the remaining part, the moment of inertia of the remaining part is equals to the moment of inertia of the first whole moment of inertia. So this is a whole moment of inertia. Let us consider this I naught, whole moment of inertia minus and the moment of inertia of the removed part. So by using this formula, we are going to find out the moment of inertia of the remaining part of the body. Suppose this is the moment of inertia of the then how can we write here? Suppose here it is nth part has removed there. Okay, so let us consider here this part is 1/4, or let us consider the moment of inertia. If it is a nth part of the body has removed there, okay, so then the moment of inertia of the removed part we can write here 1 by nth part of the moment of inertia, that is mr square by 2. Will be there, mr square by 2. Okay, so now the moment of inertia of this one, the moment of the inertia of this body, it is nth part means total will become here n times of the moment of inertia. So then from this, if we remove there moment of inertia of the nth part, so now the remaining part it will become, so how can I write there, moment of inertia of the body of the remaining part. So total moment of inertia, if it is make n parts, then total moment of inertia will be here mr square, n times of mr square will be there, no, n times of mr square. Then the moment of inertia of a whole body, so here this one n into n, so here I will come here mr square by 2 will come there. So mr square by 2. Now if you subtract from this part, the removed part it has subtracted from this one, so then we'll get the moment of inertia of that body there, Okay, by using this formula we are going to find out the moment of inertia of the remaining part of the body. Okay, so this is there in the synopsis 3, and we'll discuss now synopsis 4. It is about the torque and couple acting on the body. Then later we'll discuss the numericals from both the synopsis. So now here we see here now synopsis 4, that is about the Newton's second law of motion. And the Newton's second law, by the Newton's second law of motion, we are going to discuss about the torque and the couple acting on the body there. Okay, so now, so synopsis 4 we'll see here. Synopsis 4. So Newton's second law of motion. By Newton's second law of motion, we know that Newton's second law. So in the Newton's second law, what it will be explained there? The rate of change of linear momentum is directly proportional to the external force applied on the body. Okay, the rate of change of linear momentum it is directly proportional to this one, external force applied on the body. So dp by dt we can add there, dp by dt. Okay. So that means what there here. So then and this linear momentum, it is in the direction of the applied force. So linear momentum of the body there. Okay. So if there are a number of forces here, only the one force is acting there. If there are a number of forces is acting there, so if there is no external force acting here, then the total momentum will be 0. Okay, that says about the conservation of the body there. Okay, suppose if you see here, if you take a body here like this, let us consider a rod, a uniform rod, and on this body there are the two forces applied here. So one is upward direction, and at the other side it is a downward direction, and both are equal in magnitude, but they are in opposite direction if they axle there. Okay, so then now this body will be rotated. It will be comes into the rotation. The body comes rotate there about its axis. So according to the Newton's second law, we know that the force, external force, the rate of change of body is acting, it is directly proportional to the external force acting on the body there. So now this force, what will happen there? This force will cause for the motion of the body there. It will be changes the direction there. Okay. So now if certain body has to be rotate, there is a non-zero torque. So in the linear momentum, the force will be caused to the motion of the body. And in the rotatory motion, we are discussing here rotatory motion. In the rotatory motion, the body has to be rotated means, so there is a torque has to be applied. So non-zero torque has to be applied there. So non-zero torque has to be applied means, torque is nothing but it is a product of force and the perpendicular distance from the axis of rotation. Suppose you can say, you can take here a body. So let us take a uniform rod, and it is on this body. From the center of the body, there is a distance of r1. One force is acting there, that is a F force. And from another end of the body of r2 distance from the center, it is acting the equal magnitude, but it is in opposite direction. So when it is act there, then the rotation of the body will be takes place there. Then the net force, here the net force acting on the body is, net force will be F minus F, it is 0. F minus F, that is 0 there. Okay. If F force is means net force is 0, the motion of the body does not take place. But okay, the motion of the body may not be there. Okay, it is not there. Motion of the body does not there, but there is a effect of torque will be there. Effect of torque, turning effect of the body will be takes place there. Due to that, there is a rotation of the body will be there. So that rotation, the turning force, the equal magnitude of the forces acting in opposite direction on a body in the two directions there. So then we can say there is a couple acting on the body. Turning effect of the body will be takes place. The turning effect of the body when the two equal equal forces and they are acting in opposite direction, then that is called the torque there. So here if it is acted by, the torque is developed by two equal forces and they are in opposite direction, then it is said to be the couple. So couple acting on the body there. So when we have discussed the torque, there we have discussed this is a couple there. So now couple tau is equals to, we can write here, so perpendicular distance r1 r2 is there here. So r2 minus r1 into the magnitude of the force, we can write here, magnitude of the force. This will be gives the couple acting on the body. So this couple will be cause for the rotation of the body there. Okay. So if the body is in anti-clockwise direction, suppose it will be rotated in clockwise direction. So if it is clockwise direction means the total couple will be taken here, torque will be taken negative. If it is in anti-clockwise direction, suppose the forces are acting like this, then it will be rotated in anti-clockwise direction. That can be taken as here positive. So the torque will be taken as positive. How can we take that? So it can be taken by the right hand thumb rule. By the right hand thumb rule, we can take the direction of this torque. So torque will be represent the direction of the thumb will be represent of right hand. So whenever the plane of two forces are moving here by the curled finger, then thumb will be indicates the direction of the torque. Okay. So that is about the couple and the torque there. So now next one we are going to listen here. Understand, that is the angular momentum. It is about angular momentum. Angular momentum. Angular momentum. So angular momentum is nothing but it is a product of perpendicular distance, vector product of perpendicular distance and the linear momentum. So that is called the angular momentum. So this is the expression for the angular momentum. The product of perpendicular distance and the linear momentum acting on the body there. Suppose let us consider here an object. Suppose it is moving about this axis there, about this axis. So now if one of the particle, or we can consider center of mass of the body somewhere here, okay, and the center of mass is at a distance here r there, then center of mass of the center of mass we consider here capital M. Then, so if this body, the center of mass will be rotated about this axis in a circular path, no? So if it is moving a circular path, it will be have certain velocity, no? With certain velocity it will be moved there. With certain velocity it will be moved. Okay? The center of mass will be rotate about the axis of rotation in a circular path. So now there the angular momentum acting on the particle, it can be written as here. Suppose if it is moving in this direction, then in the direction of this there is a linear momentum will be takes place there, and here the perpendicular distance. Whenever the particle is moving about the axis of rotation, so there is a linear momentum also, it will be act in the direction of the motion of the body, means in the direction of the velocity of the body there, okay. So linear momentum and the perpendicular distance. So now the product of this perpendicular distance, cross product of the perpendicular distance and the linear momentum acting on the body is said to be the angular momentum. So angular momentum is denoted by the letter here capital L bar. So L bar, it will be the vector quantity. So now here we can write there. So L bar can be written as here. If you write it is in the normal scalar form. So L is equals to here R into P sin theta, we can write here. R into P sin theta, RP sin theta. Because you have cross product, no, cross product means we will get the RP sin theta. Okay. So now also it can be written also like this. So L is equals to R into. So here P is nothing but what there, product of mass of the body and velocity of the body with which it is rotating. So now here we can add there MV into sin theta. So R into MV into sin theta. Simply we can add here MVR sin theta. MVR sin theta. So this angular momentum will be maximum when theta is equals to 90 degrees, means if the angular momentum act on the particle perpendicular to the perpendicular distance, okay. If it is perpendicular to the perpendicular distance, then this angular momentum will be maximum there. So for maximum momentum, so here theta should be here 90 degrees. If it is theta 90 degrees between the linear momentum and the perpendicular distance, then the maximum angular momentum will be takes place, that is the MVR. That is the MVR here. MVR. Suppose if the body is rotating, so then the body will be rotated with certain velocity, and there is a radius, means there is a distance will be there from the axis of rotation and mass of the particle will be there. So in that case the angular momentum can be written as here MVR, the maximum angular momentum. Suppose if it is theta is equals to 0 degrees, theta is 0 degrees, sin 0 value will be 0, will get a minimum value, okay. So L minimum will get here 0, L minimum 0, means if it is parallel, this will be 0 there, means the angular linear momentum is parallel to in the direction of this perpendicular distance, okay. So if it is the linear momentum in the direction of the perpendicular distance, then there is no angular momentum will be takes place there. So then that will be the 0 angular momentum, it is the minimum angular momentum there, okay. So this is about the angular momentum. Now the SI unit, what is the SI unit of this angular momentum? SI unit of angular momentum we can write here distance, perpendicular distance. R is nothing but the perpendicular distance, and here the P is nothing but linear momentum. So we know that the linear momentum SI unit is what there, SI unit of here angular momentum. So that is the product of SI unit of perpendicular meter, and the linear momentum is what there, kg meter per second, kg meter per second. So we can write here that is kg meter square per second. So here the SI unit of this is a kg meter square per second. Kg meter square per second will be the SI unit of angular momentum, SI unit of L, SI unit of L. Now here next we can add the dimensional formula of L. Dimensional formula of L, what can we write here? Dimensional formula for L is equals to L is here m power 1 and L power 2 and t power here minus 1 we can add them. T power minus 1, m power 1, L power 2, t power minus 1. That is the dimensional formula of the angular momentum. Dimensional formula of the angular momentum. Okay. So this is about, and this angular momentum is a vector quantity. The angular momentum is a vector quantity. Angular momentum is a vector quantity because it is the product of both vector product of the perpendicular distance from the axis of rotation to the linear momentum. Okay. So that is about the angular momentum. And next one we are going to see here. So whenever this body is rotating in this rotatory motion there, so there is a towards the center, the centripetal force will be act there. Okay. So then what is the expression for the centripetal force? We'll see here. Okay. Generally, so now we'll see here next topic is centripetal force. Centripetal force. Centripetal force acting on the particle whenever it is rotating in a rotatory motion. Okay. Suppose let us consider here this is a body and it is rotating about this axis in anti-clockwise direction. So if the particle, if we consider here m particle if we consider, and this will be at a distance of r, and it continues. So it continues in a circular path about this axis there with the radius of perpendicular distance. Okay, with radius of perpendicular distance there. So then here, so in the direction of this, in the direction of the tangential direction to the circular path, there is a velocity will be act there. In this direction only, there is a linear momentum will be takes place there. Linear momentum will be takes place. Now, whenever it is rotating towards the center, means along the radius, means along the perpendicular direction, there is a acceleration will be takes place. That acceleration is said to be that is a AC, centripetal acceleration. Centripetal acceleration. So now we can write here centripetal force formula. We know that is a mv square by r. Mv square by r. So here we have taken smaller, so we write here smaller. And now this is equals to centripetal force is nothing but what can we write there here? Centripetal force is nothing but mass of the body into acceleration acting on the particle there, mc. Now if we equate them, we will be get here m ac is equals to mv square by r will get here. So now m and m will be cancelled. Therefore centripetal acceleration will get here v square by r. V square by r. And we have seen there in the first class, there is a relation between the linear velocity and the angular velocity. So what is the relation we got there? So that is v is equals to r omega we got. Now substitute here. So we will get here from this centripetal acceleration is, so r square omega square divided by r. So r will be cancelled here. R into omega square we can add there. So therefore AC is equals to r omega square. AC is equals to r omega square we can add there. So now the centripetal force, this AC if you write here, then centripetal force formula will get here. That is m into r omega square. M into r omega square will be the centripetal force formula. Centripetal force formula there. Okay. The centripetal force definition is what there. Whenever a body is rotating in a rotational motion about an axis toward the center of that axis there. Okay, towards the center of the axis along its perpendicular direction. That means along the radius, there is a force will be act there. So that force is called the centripetal force. The force which is acting along the radius towards the center whenever a body is rotating in a rotatory motion about an axis. That is called the centripetal force. Centripetal force. Now the acceleration. Here the centripetal acceleration we have there. Centripetal acceleration is nothing but the acceleration acting on the particle when the particle is rotating in a rotatory motion about a fixed axis, about an axis. Okay. So then along the radius there is a acceleration will be takes place on the body. So that acceleration is said to be the centripetal acceleration. And one more thing, there is a tangential acceleration also will be takes place there. Tangential acceleration along the tangent of the rotatory path in the circular path. Okay. So then that acceleration, the acceleration acts on the body whenever it is rotating in the circular path along its tangent. that acceleration is said to be the tangential acceleration. Now we'll see the expression for the, already we got there tangential acceleration formula, that is represented by at. What we got there? So dv by dt now. dy by dt means here we can write here. So d into r omega by dt we can write here. So here r can be taken out from the differentiation. So here we'll get there d omega by dt. We'll get here r into d omega by dt is nothing but what there here. That is the alpha we can write there. So here tangential acceleration here r into alpha we can write. This already we have seen there. Okay. So then the force, so tangential force, what can we write there now? F is equals to m into at we can write here. That is equals to what? M into r into alpha. This is a tangential force acting on the particle whenever it is rotating in the tangential path. Tangentially, when the body is rotating in the rotational path there. Okay. So now we are going to see here the relation between. So here we are going to see now the relation between torque and the moment of inertia. So relation between torque and the moment of inertia. Okay. So we'll see here now the relation between torque and the moment of inertia. The relation between torque and moment of inertia. Torque and moment of inertia. Moment of inertia. Torque and moment of inertia there. Okay. So torque formula is what there? Torque we can write this one, torque tau is equals to, we can write force into perpendicular distance, means Rf sin theta. Rf sin theta we can write here. Suppose is torque is a maximum there, we will get here r in f into r we can write there. So therefore simply here torque tau is equals to r into f or f into r we can write there. Okay, this is a torque formula. Okay, so now here what can we write there? So f is equals to what? Tau is equals to f is nothing but what can we write here? M into here a acceleration. So what acceleration we can write here there? Suppose centripetal acceleration, if you see here there into r we can write there. Now here centripetal acceleration formula what we got there? Centripetal acceleration, or we can see the tangential acceleration. Here the tangential acceleration we have seen there. That is a alpha into r alpha we got there. So now if you take here instead of this tangential acceleration, if I take in here, so now the torque will be takes place. Here. So now tangential acceleration at we got here r into alpha we can write now. So here if you write there, so m into, so r into alpha into r we can write there. So from this tau is equal to what can write there? M into r square into alpha we can write there now. So we know that the moment of inertia is what there? I is equals to m into r square now. M into r square. So in place of m into r square we can write here tau is equals to I into alpha we can write now. So here the relation between torque and the moment of inertia is tau is equals to I into alpha. Tau is equals to I into alpha. Okay. So this is about the relation between the torque and the moment of inertia. Torque and moment of inertia. Okay. So now there we can get the relation between, even we can get there linear momentum and the angular momentum and the moment of inertia also. That also we'll see here. So now next topic is the relation between angular momentum and moment of inertia Okay, the relation between angular momentum and moment of inertia. So here the moment of inertia, angular momentum we know formula, that is mvr no. So mvr, generally the formula is what there? Angular momentum is nothing but product of linear momentum and the perpendicular distance. So then here mvr will get there from that. Okay, So now here we know that V is what there here. V is equals to, we can write here R omega. V is equals to R omega, we can write there. Now here from this, if we write here V is equal to R omega from this, so substitute here in this equation, we'll get here M into R omega into R, we can write there. So now it can be written as here M into R square into omega, we can write there now. So we know that I is nothing but what there, moment of inertia is nothing but M into R square. M into R square, we can write M into R square. So here L is equals to, we can write here I into omega will be there. So this is a relation between, that is a relation between, so relation between the angular momentum and the moment of inertia. Relation between angular momentum and the moment of inertia. Suppose the angular momentum is constant. If the angular momentum is constant, so if L is constant there, then the relation between here, we will get the moment of inertia and the angular speed. That is here I1 omega 1 is equals to I2 omega 2, we can write there. I2 omega 2. Okay, I2 omega 2 will write there. So now here, that means what here? This moment of inertia is inversely proportional to the angular speed of the body there, or the angular speed of the body is inversely proportional to the moment of inertia of the body. That means what there? If the angular speed is greater, then moment of inertia will be decreases. Okay, and if the angular speed is lesser, the moment of inertia will be greater. Okay, that is, it has the relation between these two, linear momentum and the angular speed. Okay. So now we can see even rotational kinetic energy also. So generally the kinetic energy formula is what there? So rotational kinetic energy formula we'll see here now. Rotational kinetic energy. Rotational kinetic energy. So generally kinetic energy formula we know that. What is that? M into K is equals to mv square, no? K is equals to Ke or K. So we can write here K is equals to. So K is equals to, Ke is equals to, we can write here half into mv square, half into mv square. Half into mv square we can write now. V is equals to, we can write here R into omega. Suppose if we write here kinetic energy is equals to, so in terms of rotational kinetic energy we are saying there, rotational kinetic energy. So here we can write there R into omega into m whole square into m we can write there. So now we can write here kinetic energy Ke is equals to half into, so R square into, so m into here we can write here omega. So here kinetic energy Ke we can write here half into m into R square. So this is what we can write there. We know that here I is nothing but m into R square. M into R square is nothing but the moment of inertia. So then the kinetic energy Ke is equals to, we can write half into I into omega. Half into I into omega. This is the rotational kinetic energy. Rotational kinetic energy. Rotational kinetic energy. The expression for the rotational kinetic energy is half into I omega, half into I omega. This half into I omega is nothing but what there, we can write here half into L means the kinetic energy is half of the angular momentum also we can write there, because we got there here L is equals to what? L is equals to I into omega we got now, relation between the angular momentum and the moment of inertia we got there. So we can write like this also. So it is the half of the angular momentum. Kinetic energy is the half of the angular momentum also we can write there. Okay, that is the relation between here this one, kinetic energy and the linear momentum. Kinetic energy and the linear momentum. So here this will get here m is equals to kinetic energy formula half mv square, half mv square. Sorry, here it is omega square will come, no? This is omega square. So here also omega square will come, because here r omega square, r omega whole square. It is r omega whole square means r square, here m into omega square will come there. So here also omega square will come there. So now here what can we write there, this one? So here this equation can be written as, so half into here I into omega we can write here, I into omega, I into omega we can write there. Okay. So now that can be written as here half into L omega we can write there. This is the exact equation, because since here L is equal to angular momentum formula is what there? I into omega. Okay, that is the moment of inertia into angular speed. So now the kinetic energy, rotational kinetic energy formula we can write here half into I omega, half into L into omega. Okay, now here we got the relation between the kinetic energy of the body and the angular momentum of the body in terms of the angular speed. That is the relation between here and the expression for the rotational kinetic energy. That is here kinetic energy half into I into omega square. Half into I into omega square. Here, see, V square will come here, and here in the rotational kinetic energy, omega square will come there. Okay. What is the role of V in the linear motion, in translatory motion? The same role will be done by using this here angular speed there, omega. So here, and the mass is the role of a body in the translatory motion, and the moment of inertia will be the role of mass in the rotating body there. Okay. So kinetic energy is equal to half into I omega square will be the rotational kinetic energy of the body there. So now we are going to see here law of conservation of angular momentum. Okay. So with that we will complete this synopsis, and in the next class numericals will do from the both the synopsis there, so that we can complete this chapter. So now law of conservation of angular momentum. Law of conservation of angular momentum. Law of conservation of angular momentum. So law of conservation of angular momentum is nothing but, so from the Newton second law, we'll write here, no, suppose if it is a rotational body, external torque, okay, torque external torque is directly proportional to, torque acting in a body is directly proportional to the rate of change of angular momentum of a rotating body is directly proportional to the torque acting on the body there. That is a statement of Newton's second law in the rotatory motion. So we can write here dl by dt, we can write here dl by dt. So now if this external torque is 0, if there is no torque is acting on the body there, if there is no external torque acting on the body, then here what happens there? dl by dt will become 0. That means here dl is 0 there. dl means what there? Differential angular momentum. So that means change in angular momentum will be 0. Change in angular momentum will be 0 means here, so there is L2 minus L1 we can write now, that is 0 there. So from this what we get here? L1 is equals to L2. That means here, so whenever a body it is rotating there, when there is no external torque takes place on the system or a body there, the total angular momentum before and after action will be constant. Means total momentum before action and total angular momentum after action, it will be equal there. Or we can say here the change in angular momentum 0. The change in angular momentum becomes 0 when there is no external torque acting on a rotating body. So then the total angular momentum or the change in angular momentum of the rotating body will be equal to 0. Or we can say if there is no external torque acting on the rotating body, so then the total angular momentum before and after will be equal, or we can say remains constant there. Total angular momentum of a rotating body remains constant. That is the statement of the law of conservation of angular momentum there. If there is no external torque acting on a rotating body, so then the total angular momentum of the rotating body remains constant. That is said to be the law of conservation of angular momentum. So suppose here, and we got the relation here, angular momentum. See here, I into omega, the relation between angular momentum and the moment of inertia we have seen there. That is the relation, I omega. So now here we can write there, I1 omega 1 is equals to I2 omega 2. I2 omega 2. So from this what can we write here? So I1 by I2 is equals to, so omega 2 by omega 1. That means here this moment of inertia is inversely proportional to the angular speed. Okay. So from this we can say here, when the angular speed of the body, the moment of inertia of the body is decreases, then angular speed will be increases there. That is, here we can see in the example, like a ballet dancer when she is dancing on the floor on the rotating table. So when her hands are spreads, then the moment of inertia will be increases. Then the speed, angular speed will be decreases there. So it rotates slowly. Whenever she holds, she brings her hands near to her, then the moment of inertia of the body decreases and the speed will be increases. So of the rotating table. Okay. So that is because of this law of conservation of angular momentum. Okay. So these are the some example. Even when the swimmer is diving into the water, so what he will do there? Whenever he jumps, so he after jumping, okay, after jumps into the air, he will hold all his body near to him. Then whenever he reaching the water, then it spreads all his body. Okay, then so that is the reason why he will be goes to higher height and he will be take the safer dive. Okay, so that that happens due to this law of conservation of linear momentum, angular momentum only. Okay, so that is because here the moment of inertia has to be decreases to jump the longer height, so that after a longer height, then he has to be land in the water safely, then he has to spread, means the moment of inertia of the body has to be increased there. So that to increase that, he has to spread his body so that he will be safely land in the water. Okay, they are the examples of this law of conservation of angular momentum there. Okay, so now, so this is the concept is over in the synopsis 4, and we'll see tomorrow both the synopsis problems, so that we'll complete this chapter there. So next chapter we have the fluid mechanics. We'll see it later. Thank you, children. Have a nice day.